So thank you. I'm Leo, founder of Mika Labs, and I'm going to present the first 100 days of Fusaka after the PeerDAS hard fork. So just to start, a brief introduction about what is PeerDAS. PeerDAS is a way to increase the blob space, but without having every single node in the network to download all the blobs and to own all the data. So basically what we have here is a blob is just a space where layer 2s can put their data, their proofs of execution, etc. And so what we wanted was to increase this space. And so for that, we increase the number of blobs. But we want to do that in a way that is not expensive for the nodes in the network, and so that they don't have to download every single blob of data. So what we do is we extend the blob data with rich Solomon encoding. And then what happens is that the nodes only need to download some part of the data, specifically some columns, in order to guarantee that the data is still available. Now, some nodes in the network, if they are big nodes in the sense that they are running many validators, or, for example, because you are running a node explorer or something like that, you can download all the blob data, so all the columns. And in that case, you are considered to be a super node. If not, then you only download a certain number of columns, and that is fine. So this is what we call PeerDAS, basically. This was developed a couple of years ago, and it was released in the Fusaka hard fork in December. And what I'm going to show is, what has happened since that fork. So here's the timeline. We had the hard fork on December 3rd, and then we had two BPOs. BPO is an acronym that stands for blob parameters only. So those were 2 points in time, just 3 days after the hard fork. We increased the number of blobs, so that was BPO 1. And then 1 month later, in January, we increased the number of blobs again, what we call BPO 2. Now, just about 40 days after the hard fork, we did an analysis about how things were going on the blob space. And the things were not going very well. I'm going to present that. And then, so we did another checkpoint, which was 100 days later after the fork. And in this case, the data improved a little bit. So I'm going to present first the 40 days checkpoint, and then the 100 days checkpoint. So this is a little bit of a busy picture. Let me explain to you. What you have on the x-axis is the time. So from October till January. The green line that you see, that you have in the middle, is the Fusaka hard fork. And then just after that, you have the purple line, which was the first BPO increase. Now, what you have in every column here is 1 day, and what this box plot is showing you is the average of number of blobs that you had in that day, the average and the minimum and the maximum. So you see that after the first BPO, we increased the maximum from 9 to 15 blobs, and the target moved from 6 to 10, right? And then we had the second BPO, which was in January, and we increased the target to 15 or 14 blobs per slot, and the maximum to 21. So that's the second increase that you see on the right. And the red line shows the number of missed slots in a day. So we had actually a really bad day just during the Fusaka hard fork, just after the hard fork. But then we recovered, and we can see that it's a very low number of missed blocks. Sorry. So if we look at the total number of blobs per slots in this figure, from 0 to 21, which is right now the maximum number of blobs that you can publish in a slot, we can see that only about 0.1% of those slots have more than 16 blobs. Okay? So that means that in the first 40 days after the Fusaka hard fork, we were pretty much not using any of the space that, that we had available. Very, very little number of slots had more than 15 blobs. Now, if you look at the number of missed slot after a specific slot with a high number of blobs, then you see something like a figure like this. But it's hard to see it, so we normalize it by dividing the total number of missed slots in comparison to the number of slots with that many blobs. And what you can see here is that in the first 40 days, when you had a slot with 15 blobs or more, you had a much higher probability of missing the next slot. That means it was about 3 times higher the probability of missing the slot if the preceding slot was having more than 15 blobs. So that was really worrisome at the time. And actually, this was due because to one of the clients was having some issues with the database. And when you had a high number of blobs, then that was triggering some delays, and then you had a much likelihood case of missing the next slot. So that was the situation 40 days after Fusaka hard fork, and that was a little bit worrisome. And then we did the same tests 100 days later, and this is what I'm going to show now. So if you look at the figure here, this is 100 days of Fusaka, and we still see that the utilization of blobs is very, very low. So we have a capacity up to 21 blobs, but very rarely we are using that capacity. And even up to this morning, I was checking, and the average number of blobs per slot was like 4 or 5. And the target right now is 15. So we are really not using the space that we have. Now, it has been quite some number of months since the Fusaka hard fork. It's understandable that layer 2s will take the time to adapt and start really using the space that they have. But it has been about 5 months, and we are still not seeing the usage of the blobs increase. So it's an open question what is happening there. It's not clear to me at this point. But I hope that soon we are going to start using the data that the space that is available for Ethereum. And then we also did the second analysis, which was to try to check what is the likelihood of missing a slot after a specific number of blobs. And in this case, we saw that the correlation that we previously observed was not there anymore. So basically, you have exactly the same probability of missing the slot, whether you have 0 blobs or 15 blobs or 20 blobs in the preceding slot. So that is a good thing. That is good news, because that means that we are not having network issues or anything like that. That is really completely overloading the nodes for some reason. So that was good news. So basically, in summarize, if you have to remember anything of this talk, there are 2 things. First of all, the good news is that we don't see any correlation between missed slots and the number of blobs at this point. Okay, so that's the good news. The bad news is that we are still not using the space capacity that we delivered with Fusaka, and it's still unclear why this space is not being used. Now, there are a couple of things that should come in the near future, and actually Daniel is going to talk about that just after this talk. We are changing the way we transmit data over the network. Right now, we are sending data in full columns, which is okay-ish, but it's not very efficient. And there are many, many things that we can do by sharing partial data, partial columns, instead of the full columns. But I'm not going to talk more about that. Daniel will present it. And I think we also should start thinking about transitioning to a 2-dimensional PeerDAS strategy, which was actually the original DAS idea that was developed years ago. The 1D PeerDAS scheme that we are using today was supposed to be temporary, and this should increase the reliability and the robustness of Ethereum in the long term. So I still think this is important to do, although, of course, there are many, many other things that we are focusing right now. We are working on EPBS for Amsterdam. Fossil is coming for Hegota. So there are many things on the pipeline. But I think it's important to not keep, to not forget about this in the future. Now, there is one more thing that we need to do, and hopefully we can do this before 2032, which is the time where we expect to have the first quantum computers that are capable of cracking the signatures that we use today. One of the cryptography tools that we use for DAS is KCG commitments. KCG commitments can be cracked with quantum computers. So that means that the current scheme that we are using for PeerDAS is not quantum proof. We have some ideas about how to fix that. We have explored something that is called FRIDA. It's a quantum proof cryptographic scheme that allows us to tolerate, that is quantum resistant, basically. But it also introduced several difficulties that we still don't know how to solve. So it's not a complete solution yet. The good news is we still have several years, hopefully, to do this research. But yeah, it's important to start working on this. And yeah, so this is more or less the state of PeerDAS today and what we expect to have in the coming years. And that's it. That's it for me. You have questions, I'll be happy to answer. Thank you.